Welcome to part 2 of Graphs of Polynomial Functions, where we focus on what's happening near the origin. So in the last video we focused on what's happening away from the origin, the end behavior, when x is getting really large to positive infinity or really small to negative infinity. But we also want to know what's happening near the origin. And we get a couple of things near the origin. First, you just see again our definition for polynomial function here. The things that we get that are close to the origin are the x-intercepts, which we also call the zeros of our function, the y-intercept, and any local max or mins that occur. So we're going to start with the real zeros of polynomials. So the following things are equivalent for a polynomial function p of x and some real number c. So if we say c is a zero of p of x, that's the same as saying that x equals c is a solution of the equation p of x equals 0. And that's also the same as saying that x minus c is a factor of p of x, or that c is an x-intercept of the graph of p of x. So let's take a look at an example of two functions. Now these two functions have already been factored. So if we want to determine the real zeros of these functions, we could do a couple of things. We could replace f of x with 0 and then solve for x. But we also saw, if I just go back to the previous slide, that if x minus c is a factor, then c is a 0. So we can just take the opposite sign in that factor, and that we know is a 0 of the function. So here we have 3 zeros, one for this factor. So we could think of that as x minus 0, which means that x equals 0 is a 0. Here we get the 0, positive 3, and here we get the 0, negative 1. So once again, we have zeros at 0, positive 3, negative 1. For the second example, we're looking at f of x equals x plus 1 squared times x minus 2. Again, this has already been factored, so we can find the zeros by taking the opposite sign inside the factors. So we have a 0 at negative 1 and at positive 2. Now let's also graph these two functions just to see what's happening. I have them both entered in my graphing calculator here. I'm just going to graph the first one. So the first function is turned on, the second one is turned off. And I'm graphing in Zoom 4 right now, Zoom Decimal. Alright, so I'm pretty close to the origin here. Again, I'm just focusing on the zeros, which can also be interpreted as x-intercepts. And in this first case, I have a 0 at negative 1, at 0, and at positive 3. In the second function, so let me turn this one off, and I'll turn the second one on and go ahead and graph that in the same window. I see I have a 0 at negative 1 and another 0 at positive 2. Now, something interesting happened here. The 0 at negative 1, my graph kind of bounced on the x-axis, and the 0 at positive 2, it just kind of passed through. So that's actually something that we can determine by looking at the factored form of our functions. If we look at this function here, we see that that factor was repeated twice. So we have what is called a multiplicity of 2. And that exponent, or that multiplicity, is going to tell us about whether a graph is going to bounce or whether it's going to pass through. We could think of these other parentheses as having exponents of positive 1. So let's just summarize multiplicities of zeros. So again, when we're talking about multiplicity, if we look at the factored form, we're talking about the exponent on the outside of the parentheses. So here, if c is a 0 of even multiplicity, that means the exponent outside the parentheses is an even number, and that will tell us that the sign of the function does not change from one side of c to the other side of c. So it's either positive and then positive, or negative and then negative. The effect of the graph is that it bounces on the x-axis at C. Now, if C is a 0 which has odd multiplicity, so the exponent outside of the parentheses is 1, 3, 5, or any odd number, that means the sign of the function is going to change from one side of C to the other. So on one side it's positive, but on the other side it's negative. And the effect on the graph is that the graph will cross through the x-axis at C. So if I go back to my graph here and go back to the example, so again, this is the example that we see here. This 0 at -1 has multiplicity 2. 2 is even. We get a bounce. This 0 is at +2. It has multiplicity 1. 1 is odd. It goes through the x-axis. So there's some other things we can get from the graph, or actually the equation of our polynomial. We can determine, just by looking at the equation, how many local maxima or minima we will have. Now these are also called turning points or local extrema. If your polynomial has degree n, then that polynomial will have at most n-1 local extrema. So for example, if we're given this polynomial function x to the 4th plus x cubed minus 16x squared plus 3, the degree of this polynomial is 4, which means we have at most 3 local extrema. So that means at most 3 peaks and valleys, 3 maxes and mins. There could be less than 3, but there cannot be more than 3. Alright, so let's put this all together and think about everything we've learned so far about how to get information from the polynomial function and what that tells us about the graph. So we're looking at this function, f of x equals, I'm giving it to you in factored form, 4 times quantity x plus 5 times quantity x minus 3 squared. So we want to list each 0 and its corresponding multiplicity, determine the end behavior, so this we talked about in the first video, determine the y-intercept, determine the number of local extrema, and then we'll make a quick sketch of the graph. It's going to be a really rough sketch because we really can't get all of the information of the graph by just these characteristics. Alright, so here's our function once again. First thing we want to do is determine the zeros and the multiplicities of each of those zeros. So looking at our factors, we have a 0 of negative 5. The exponent is 1. It's odd, so that means we cross over the x-axis. Here we have a 0 of positive 3, has multiplicity 2, which means that we bounce on the x-axis. Alright, so the next thing we want to do is determine the end behavior. This means we have to look at the leading term. That leading term is going to come from multiplying the 4 times the x to the second power. If we had multiplied all of these together, that would be the first term, 4x to the 3rd. So we have an odd exponent, and the coefficient is positive, which means we're going up to the right and down to the left as our end behavior. To find the y-intercept, we want to find f of 0, which means we're just setting x equal to 0. So everywhere I see x, I'll plug in 0 and then just simplify, which means I'm multiplying 4 times 5 times negative 3 squared. And when I do that, this is just 20 times 9, which is 180. So I have a y-intercept which has coordinates 0, 180. Okay, the next thing I want to do is find the number of local extrema, which means I need to look at the degree of this function. I've already found the leading term to be 4x to the 3rd, which means the degree is 3. Subtract 1, and that means I have 2, or at most 2, local extrema. Alright, so we're going to take this information and create a quick sketch of the graph. So I'm not really going to label much of a scale on here. I'm just going to put the values that we found so far. So we have zeros at -5 and at +3. So I'm just labeling those on my x-axis. Again, it's just a sketch. It's not anything super accurate. My y-intercept is at 180. So I'm going to put 180 fairly high up on my y-axis. And I'm going to plot points at each of those places because I know that that's where my graph is touching. Those are my x and my y-intercept. Now I also know about my end behavior, so this graph is going to start from the bottom and come up. It's going to hit that. It's passing through because it crosses. It goes up at some point. It's going to hit this y-intercept. It's going to come down, bounce at 3 because 3 has a multiplicity of 2, and then it's going to turn around and go back up. Again, I'm looking at all of these things together. The end behavior, it goes down and to the left, up and to the right. I know it has to cross at -5, bounce at 3, and at some point it's going to pass through 180 on the y-axis. I also know that I can't have more than 2 local extrema, and the way I've drawn it, I have a local max here and a local min here, so I have not violated that aspect. Notice I have no idea how high this graph is going, so I'm really just creating a very quick sketch. I don't really know how far up that max is. It could be at the y-intercept. Again, I'm not sure without finding out some more information. I do know that I have a local min here because it is bouncing at the x-axis, so I know that has to be my local min. Okay, so that concludes our video about graphing polynomial functions. If you have not watched part 1, please go back and watch part 1 so that you have all of the information that we needed to answer that last question.